So, so as I have mentioned, Professor Pal has already started this topic. So, and of course, from your 12th standard mathematics course, you have little idea about ordinary differential equation. So, I will today start a different part from ordinary differential equation. So, I have now shared the PPT. I hope all you can see the PPT, right?
Yes, sir.
Okay, okay.
Yes, sir.
Okay, so before I start my class, let me tell you a few things. During the class, don't make any noise. Try to listen carefully. Okay. And whatever the doubt you have, you please note down and ask me later at the before the end of the class. And I will definitely answer all your questions. Okay, so my suggestion is better you first listen me. Okay. So here I have made the slide and I will definitely upload that after the class in MS Teams so that you can download it and you can go through the note. So in most of the places I have I have included in this slide with my handwritten note. So if you face any difficulty to read this handwritten note, you may immediately ask me. I will definitely clear your doubt. Okay, but I have tried to write in a better way, but maybe you cannot follow the slide properly, then immediately ask me. I will definitely talk to you. So the another topic from ordinary differential equation that is a part of our course, which is linear differential equation of higher order. Linear differential equation of higher order. So as I have mentioned, Professor Paul will go through the first order ordinary differential equation, and he will cover the first order ODE of different type. They may be linear in nature, may be linear, may not be linear. Okay, so he will cover all those things. Okay, but I will consider only here the second order or higher order differential equation. Okay, so first we will consider linear differential equation. So let me define the differential equation first, and then I will say, when the equation will be nonlinear. So let us write down the general form of linear differential equation of order n. I hope all you know the degree and order of the differential equation. So please don't make noise. Okay, so let me mean to you all. Don't make noise. Okay. So here I have written the linear differential equation of order n. Why this equation is order n? You can see the highest order derivative in this equation. This is what the differential equation that I have written here. So highest order derivative is n. So you can say it is a differential equation of order n. Okay. Now why it is linear? See here, this equation involves three coefficients. See here, the coefficients are P1, P2, so on Pn. Okay. So here we will first of all consider all these P1, P2, so on Pn, that is Pi. They will be considered as any function of x or constant. So in Pi, there will be no term involving y or its derivative of any order Okay. And another thing, if you see the derivatives in all the terms, the degree is 1. Okay. So since Pi are constant or function of x, since they are not involves directly y or its derivative, and the power of all the derivatives, see here it is 1, here it is also 1. So these are all linear. The derivatives are appearing here are all linear. So then we can say this equation is linear differential equation. So when it will be nonlinear in nature? One of the possibilities, let's say P1, P2, Pn, they may be function of y or derivative of any order. Or maybe let's say you are considering a differential equation of this form. Let's say d2y dx2 square is there. So power is not 1 plus y into dy dx. Or see here, in the second term, you have y into dy dx. Okay, so the coefficient is function of y. So these kind of differential equations are known as nonlinear. But in your course, we have for higher order differential equation, we have only the linear differential equation. So here I must say you, the differential equation is a big topic. This is introductory course. So in this particular semester, you have nonlinear first order and linear first order differential equation and linear differential equation of higher order. So we will not consider in this course the nonlinear ODE of higher order. We will not consider this in this particular MSc 02 course, Maths 2 course, but in future, in your next semester, you have again differential equation where we may talk about nonlinear differential equation. So for the time being, we will restrict ourselves with the second order, non second order, but higher order maybe, but linear differential equation. We will not consider any nonlinear differential equation in this course. Okay. But that is, of course, a very important part, and that is not in this course, but subsequently next semester we'll go through the nonlinear differential equation. And in mathematics department, we offer several different courses related to differential equation. Later on, you can join those courses to learn this differential equation more clearly. Okay, so it's a big course. It's just in your Maths 2, we have included a part of that ordinary differential equation, just an introductory course you can think about this course. But still we need to learn many things. Okay, so for the timing, we'll restrict, as I have mentioned, for linear differential equation of higher order. Okay, so first and foremost, what a very particular situation we'll consider that I have highlighted here. That we'll first consider the differential equation for which these coefficients mentioned here, P1, P2, Pn, these are all constant. These are all constant. Okay, these are all constant. That differential equation first of all we'll consider, and subsequently we'll consider a typical type of differential equation for which these are not constant but a typical form of function of x. That I will discuss subsequently. Let us see first how to solve this differential equation when all these are constant. So there is a name that we often relate to this case, that is this differential equation for which the coefficients are constant are known as linear differential equation with constant coefficient. In your syllabus, you can see this terminology we have used there, linear ordinary differential equation with constant coefficient. Okay, so we'll first consider this particular case. Now, there is a complexity in this equation still. See, the right hand side, there is a function capital X that I have mentioned here. So in general, we consider this capital X is any function of X. This capital X is any function of X. Okay. So one possibility is, of course, constant. Another possibility is any function of X. Any different, of course, here we will consider any differentiable function of X, differentiable sufficiently. Okay. So one possibility, very simple possibility is, let's say it is 0 or any non-zero function of X, or any non-zero function of X. So we can classify further this differential equation that I have mentioned here, the linear ordinary differential equation with constant coefficient. We can classify it further considering X is 0, right hand side is 0, and right hand side is any function of X, any sufficiently differentiable function of X. So we use this term homogeneous. Homogeneous means if X is 0. Okay, so we can classify this differential equation of this form, linear ordinary differential equation with constant coefficient, into two parts. One is homogeneous differential equation, another is, of course, non-homogeneous. Okay, so homogeneity means right hand side is 0. Okay, so then the equation that we have written earlier, this takes the very simple form, that is right hand side is 0. Only the difference between this equation and equation 1 is right hand side is 0. Okay, and of course, as I have mentioned, first of all, we'll consider these coefficients P1, P2, Pn. These are all constant. So first we'll go through how to solve this equation 1. Okay, then we'll extend the idea to consider non-homogeneity. That means right hand side is non-zero. Okay, with the help of the solution of equation 1, we can further extend the technique to get the solution of non-homogeneous differential equation. Okay, so I guess in your 12th standard, you have, you know, a little bit about how to solve homogeneous equations. So I will revisit all those things first. And the main complexity here is to how to consider the non-homogeneity. Then subsequently, I will discuss how to consider the non-homogeneous differential equation. Okay, so this is all about the introduction towards the linear differential equation of higher order. Now we'll consider how to, we'll go through how to solve this equation. See here, in differential equation, main challenge is how to solve them. how to solve them. So systematically we'll move towards to consider more complicated problem, but first of all we'll restrict ourselves particularly in this course that linear differential equation, but equation can be of any order but finite in nature. So the question here is how to solve this equation 1 that I have stated here. This is homogeneous in nature. I am again repeating. So for this type of equation, we often consider a trial solution. The trial solution that we consider y equals to e to the power mx. The question is why we always consider y equals to e to the power mx as trial solution. To understand that, we have to go through one theory. See here, that let me highlight that one, and then I will say why e to the power mx is the most suited trial solution. See, we can have various function like cosine x, sin x, or x, any polynomial in x, or any other function, 10x, cot x. Okay, so we have various elementary function. So out of all those various elementary functions, we choose the trial solution as y equals to e to the power mx. The idea here is you remember one thing always, that if you have a differential equation of order n, then there will be n number of linearly independent solution of it. Okay, I will, in this particular course, we have a topic that is linear dependence and independence. There we will discuss in details about all those things. Okay, but the idea here is linearly independent function means what? Let's say you have two functions. One is, let's say f1x and another one is f2x. Okay. So linearly independent means one cannot be obtained by a linear combination of the others. Let's say, let me give you an example. Let's say you have a function x and another function c1x. So see, this f1 and f2, they are related via a constant coefficient. So one can be obtained from the other one by a constant multiplier. So they are certainly not linearly independent. They are basically linearly dependent. One depends on other. But if you consider x and x square, so x square cannot be written as a constant multiplier of x or vice versa. So they are linearly independent. Or if you consider e to the power x and e to the power minus x. So let's say you have two functions, e to the power x and e to the power minus x. So you can see one cannot be obtained from the other by a constant multiplier. Okay, so these functions are linearly independent. We have a separate part of this particular course, how to check linearly dependent, independence, and all the things related to these two type of function we'll discuss subsequently. But the main idea is when we have a nth order differential equation, we can expect that the differential equation must have n number of linearly independent solution. Now see, the mathematical benefit to consider y equals to e to the power mx. Then I will come to that fact why we choose e to the power mx. Okay, so let us consider for the time being y equals to e to the power mx is a solution. So you can easily find dy dx, d2y dx2 and nth order derivative also. The main beauty here is with e to the power mx is the derivative of e to the power x is always e to the power x. So if you consider e to the power mx, there will be a factor m into e to the power x. When you calculate dy dx, there will be a factor m to the power n into e to the power mx. So if you substitute all of them into the equation 1, then what you can write, see here, you can write like this, m to the power n plus p1 m to the power n minus 1 plus so on pn e to the power mx is 0. And all you know, this function e to the power mx is non-zero always. Okay, for any x. So what you can say, we can form a polynomial equation in m. Okay, now see, this is polynomial equation of m of order n. Okay, it is polynomial equation, polynomial. Okay, so all you know, if you have a polynomial equation, then from the fundamental theorem of algebra, that these polynomials should have at most n number of roots. Exactly, better to say exactly n number of roots. They, if you consider p1, p2, so on, pm are real number, the root may be real, root may be a number from extended plane like complex. Okay, so it ensures always that you will have different n number of root. Let's say m1, m2, so on, mn. So you can always expect n number of root out of it. And each mn, that means m1, m2, so on, mn corresponds one solution. That means you can always expect n number of, exactly n number of root e to the power mnx for all n varies from 1 to so on. Okay, and this range will be up to the order of the differential equation. So it means that with the choice of e to the power mx, we can always find exactly a number of linearly independent solution. That means this choice, that is y equals to e to the power mx, the trial solution that we are considering, it covers all the possibility of the solution. All the possibility of the solution. So that's why we always consider, I mean, compared to other elementary function, we always consider y equals to e to the power mx as the trial solution. And with the help of this trial solution, you can form an algebraic equation, rather to say polynomial equation, that is given in equation 2. This equation is termed as auxiliary equation. And for the fundamental theorem of algebra ensures that you will always have exactly n number of roots, and each roots corresponds one solution of the homogeneous equation that we have considered right here. Okay, so that means we can expect to have all the solution by choosing the trial solution as e to the power mx. Okay, so let me highlight this with some example. Let us consider a very simple example that I have considered here. Then I will consider different cases
Can
that
you
I have
repeat that
mentioned.
nth solution part, that we will get n solutions of this
Yeah. So
equation?
do you know polynomial equation?
Yes, sir.
Okay. So let's say you have polynomial. How many root? Polynomial of degree 2. How many root you can have?
2.
2.
Okay. If you have n number of a polynomial of degree n,
n.
so n. So that means you can always find m1, m2 from this n number of root, right?
Yes, sir.
Yeah. So that means you can always find n solution. N number of solution. We have to now look into it that whether they are linearly independent or dependent. If they are linearly independent, we are done with the solution. Because for any nth order differential equation, we can have always a number of linearly independent solution. Okay, so let me illustrate this one, then it will be more clear to you. Okay,
Okay, sir. Thank you.
with some example. Okay, so see here, I have given you a very simple example, included here a very simple example where the coefficients are constant. So these are constants and right hand side is 0. So you can say it is linear second order differential equation with constant coefficient and homogeneous also. So we have considered a trial solution e to the power mx. So if you write e to the power mx here, then d2y dx2 will be m square into e to the power mx, and this term will be 3 into m into dy e to the power mx, and this term will be minus 2054 into e to the power mx. You may write here e to the power mx also, and since e to the power mx is non-zero, e to the power mx is non-zero for all x, so you can drop this term. You can write then the auxiliary equation as m square plus 3m minus 54 is 0, and you can get the two roots of m. See here, you have
Yes.
second order differential, sorry, second order polynomial equation, two roots are there, right? So one solution, then you can say one solution will be e to the power 6x, m value is 6, another solution will be e to the power minus 9x. Okay, now see e to the power 6x and 9x, one cannot be obtained from the obtained from other by a constant multiplier. So you can say they are linearly independent. I will discuss this independent part later on, and we will set up some theory. But idea is the two functions are said to be linearly independent if one cannot be obtained from other one by a constant multiplier. That you can see from this example, right? So these are two solutions. Now, if you want to write the general solution, so general solution will be what?
M
Linear
minus 6 into m
combination.
plus 9.
Yes, this is what the linear combination. You can do this because the equation is linear in nature. Okay. Since equation is linear in nature, so you can write the solution as linear combination of two solutions. Okay, so this is called as the solution of the homogeneous differential equation. Sometimes we call it as complementary function. I will definitely discuss this term subsequently when we will consider non-homogeneous equation. Okay, but this is what we know as complementary function.
Sir,
Okay.
one thing.
Mhm.
Sir, how are you able to represent it in like C1 e to the power 6x plus C2 e to the power?
Yes. Your question is very good question. Let me tell you what is the equation that you are considering here. It is linear in nature. Linear in nature, right? Now, or see the example that we have considered. This one. This is linear in nature, right? There is nothing non-linearity because d2y dx to power is 1, dy dx is 1, y is also, there is no multiplier like dy dx. So this is linear in nature. Now see, if you say e to the power 6x is a solution, just take a constant multiplier, whether it will be a solution or not. That will be a solution. It is linear, right?
Yes.
And what
Yes,
about
sir.
C2? Yeah. So what about C2 e to the power minus 9x? Is it a solution or not? Since e to the power minus 9x is solution, then C2 into e to the power minus 9x will be a solution. Right?
Yes.
So you
Yes,
have two solutions. One is y1, let's say this is C1 into e to the power 6x. Another one is y2 is C2 e to the power minus 9x. So what about
Sir, why
y1?
we are adding?
Why we are adding why we are considering constants?
No, sir,
That
why
is
we
your
are
question
adding
now?
these two, sir, these two solutions to make
Okay,
this
okay.
solution?
So you start with a term, let's say y equals to c1 e to the power 6x and c2 e to the power minus 9x. Can you form the differential equation eliminating c1, c2? Just opposite part, think about. In your 12th
Yes, sir.
standard, yes, you have.
Yes, sir.
So
I,
what will be the
I did.
equation?
I did by dy by dx is equals to c1 in e raised to the power 6x
Sir, two
into
arbitrary constant, the double differential. Yes, sir.
This
Second
will
def.
give you this
Sir,
one.
we'll get the same
Yes, sir.
equation.
yes, yes.
Yes, you will get this equation, right? If you
Yes, sir.
eliminate C1 and
Yes, sir.
C2, you will get this equation. Okay.
Yes, sir. Yes, sir.
So in second order, okay. So you know the other part actually that if you have two constant, if you eliminate, you will have second
The
order
degree
differential
order
equation.
will be 2.
Yes. So that means any general solution of second order differential equation will involve two constants.
Okay, sir. Now it's clear.
Yeah, so that means you will have a family of curves where there will be two parameters, C1 and C2. If you have third order differential equation, likewise, you will have three coefficients, three constants, C1, C2, C3. And in that way, you can extend. So in your 12th standard, you learn the other part, how to form the differential equation. Now it is how to solve the equation. Okay, so if you have second order differential equation, general solution must constant to coefficient. Okay, if you have third order, accordingly you want to increase the coefficient. And idea here is that I was discussing actually that you
Sir,
have two
always,
solutions. Yeah, sorry.
sir, always we have to consider the addition, or at the worst cases, there may be the case at we have to do minus like c1 e power 6x minus. So that's why we get the our first equation.
Addition and subtraction, does it differ? I mean, if you consider C1 into e to the power mx plus C2 into e to the power minus mx, or if you change the sign of C1 and C2, does it make any change? You can
Like
adjust them.
multiply is also there.
Huh?
But no change. The constant sign will change then.
Exactly. So
Yes,
these
sir.
are arbitrarily chosen constants. So you can write it as C1. Here you can put a negative sign, but that makes no sense. It is actually a sum of it.
New
You can
constants.
adjust it by a new
So
constant.
if I
New
do
constant.
so no sir. So if I do multiplication and c1 c2, I consider that another constant. So we done like that problems in place 2. That's why.
Sorry, you want to multiply these two solutions.
Yes, sir, and we can consider C1 and C2 as another one like K constant. Like some problems are there in
No,
place too.
how
That's
can you multiply? Just see here you have, this is one solution, another one is y2. So add them to get the general solution. What is your question? Whether we can multiply y1 and y2?
Yes, sir.
Is
Yes,
it
sir.
your question? You
Yes.
just consider a different equation, then see. Let's say new equation you are considering, y equals to c1 e to the power 6x into c2 e to the power minus 9x. What will be the case? Then c1 c2 e to the power minus 3x. So you can treat it as c3 e to the power minus 3x. What will be the order of differential equation if you eliminate c3?
Sir, 1.
1.
What?
Whether it will be same as the equation that we have considered? Of
No,
course,
sir, it
no.
will
No,
contradict.
sir. No.
So
Yes, sir. Got it.
why that question comes in your mind that you will multiply? See, multiply means you will have only one constant. So there is no chance to have this equation back. Okay. So if we are dealing with linear differential equation, just find two solutions, add them to get the general solution. I mean, consider the linear combination. It is called as the linear combination of both the solution. That is also a
Sir, if the
solution.
order will be 3, then 3 solution will come.
Yes, that I will highlight. This is trivial question that if order is 3, 3, because see, we have mentioned that if you have nth order differential equation, how many roots are you have? N. So if you have n number of root, accordingly your solution will be C1 e to the power m1x plus C2 e to the power m2x plus so on Cn e to the power mnx. I
Sir,
will
one
cover, just listen me. See, you might have various questions at this moment. Some of them are very simple, by the way, but see, I always motivate the student to ask me the question, but better, see, I am going through the stuff now. I will cover all of your doubts. Okay. Just listen me first, and I will definitely cover all of your doubt. Okay. I have prepared my slide and I am delivering the lecture in that way. I am not asking you that don't ask me the question, but better you listen me first. I will definitely give you a chance to ask me the question first. See, some of the things that maybe I can cover by while giving the lecture, so there is no need to ask the question. Then it will be just repetition of the thing that I am discussing. Okay, so better please listen me first. Okay, then you please ask me the question. That will be perfect for me and for you also. Okay.
Excuse me, sir.
Yes, again. What happened?
No, sir. Sir, not a doubt, sir. Sir,
Oh.
actually, there is a problem regarding the link. Sir, many students have joined, but they are not in this particular room, sir. They are in some different class.
See, generated the link. You can see the link in your MS Team account from where I have joined, and I have allowed all of your friends.
Yes,
Okay.
sir. But at
Yes,
least
sir, yes,
20 to 25 students are there.
Sir, with same meeting names as two classes have been started, so students are entering
sir.
the same class and they are not able to attend the class.
Free meeting.
Yes,
Yes, sir.
How it is possible?
Don't know, sir.
With a
Sir, they are
simple
join.
link.
Sir, some
Sir,
yes, sir.
students
they are,
started the
sir,
meeting by themselves.
sir, they are joining through the same link, but they are going to some different class, sir.
Oh, this is first time. I don't know how MS
Sir,
Team works,
sir,
but
maybe if you have some access, kindly end all the other meetings and kindly keep this meeting only if you have
let
time.
me see. Okay, let me see if I can do that. I never faced this typical issue earlier. Okay, let me see. Ask them to join today's meeting link. Wednesday that I have started from 12. Okay, ask them
Yes,
to
sir.
join
Yes,
it.
sir. They have joined in the same link, but they are arriving in some other room, sir.
Oh,
The problem.
Yes, sir. They are joining through calendar only.
no,
Yes, sir.
ask them.
Yes.
In your account, mathematics 2 MSc 20 MSc 02 section name was given. There you can see a link is reflecting. Okay.
Sir,
So,
all late callers bypass the lobby.
uh, okay, let me then leave from this meeting and let me join from another. From the same link, whether I am coming back to this platform or not. Okay, let me see. I never faced this issue. Okay, so I don't know actually.
sir.
Just
Instead
a
of
minute.
that, bypass the lobby, sir.
Yeah, I
Yes.
have bypassed the lobby right now. Let me. Okay, bypass. Okay, okay. Now, see, I have bypassed the lobby now.
Sir, don't leave the meet, sir. Then you will go to some other meet and we will be sitting here waiting for you. This happens frequently.
Yes, sir. Don't leave, sir.
Sir, they will
Sorry.
see the
Sir, just
recording.
try leaving and then joining again. I mean,
What to do? Should I leave? I never faced this issue
Yes, sir.
earlier.
Please
I
rejoin,
mean,
sir.
last
Sir,
2
you
years I
can
never.
join again.
No, sir.
Don't
No, sir.
leave,
You
sir.
don't
It
leave,
will be
sir.
only
Sir,
Sir,
time
don't
but
waste,
leave.
if
sir.
you leave, we will go to another meet and we will stay in this meet, sir. Like that
Yes.
happens in earlier
Sir, only
classes.
time waste will happen, sir. Don't leave.
Don't leave, sir. Sir,
Sir,
the
only
ones who are not able to,
Don't
they
leave.
can view the
See, I
recording.
have.
Sir, let
What?
us continue the
Yeah, yeah.
with the class. The recording will be
Yeah.
available, and for next
I
class we
think
will reset
yes,
that.
yes. I think that will be perfect. Actually, see, ask them to join via today's meeting link. They might have joined via the link that was created by Dr. Paul. I can see here some of your friend has joined via the link created by Dr. Paul. They have joined the class scheduled on Tuesday, and some of your friend has joined the class that was scheduled on Monday. So how can they join in my class with those links? Ask them to join via my link that I have created today. Okay, so that's how we can resolve the issue that I can see from here. Okay, so if anyone tried to join via the link that I have created today, they can appear here. Okay, so they might have done that mistake. It not like
One
that
way
with a
is that
single link, two
to
meetings
delete the
are going on.
previous class.
They
sir,
might
they are
have
getting
joined.
redirected to another meet
No,
using the same
I am
link
not
only.
sure. I mean, I can
Okay.
see from here they have joined via different link. Okay, ask them to join via this link that today I have created. Okay. Anyway, let us continue the lecture. I mean, I have bypassed all of your friends, so they will accordingly join if they wish. Anyway, so where I have stopped. Okay, so the idea was, okay, so we have considered a typical situation here. The coefficients m1, m2, I mean the roots m1, m2 that we have considered in this particular example, they are distinct, real and distinct. Okay, so for this case, when the roots are real and distinct, okay, when the roots are real and distinct, you can see from here that I have mentioned, let's say m1, m2, so on mn, these are real and distinct. All you can understand the meaning of real and distinct. So then the general solution will be c1 e to the power m1x plus c2 e to the power m2x plus so on cn e to the power mnx. Okay, the linear combination of all the solution, that is e to the power m1x, m2x, and so on e to the power mnx. These are the solution, and linear combination is given in equation 2. So you remember, you can only write the general solution in terms of linear combination. Okay, don't consider any product of it's c1 e to the power m1x and c2 e to the power m2x. That makes no sense. You can only consider the linear combination of all the solutions. Okay, that will be a further a solution since the equation is linear in nature. You can do that because of the linearity property of the differential equation that we have considered. So this is what the example for real and distinct case. Next is, let's say the auxiliary equation has some of its roots are real and distinct and some of its are not distinct. I mean, some of them are real and equal and some of them are real and distinct. So let's say m1 equals to m2 and rest of them are unequal. So two are same. That is, first two are same, m1 equals to m2. Okay, likewise, we can extend this idea to consider first three are same, others are distinct. Likewise, you can consider, let's say m1 is m2 is equals to m3 is equals to m4, and rest are same, if distinct. m5, m6, and so on, mn are distinct. So likewise, you can extend all these, all the possible cases. So if two are equal, then let us think about first distinct situation. That is, e to the power m3, that will be a solution. E to the power m4 will be a solution, and e to the power mn will be a solution. So linear combination of all of them will be a solution. Now, what about the equality? So one root, if you say m1x, second root is also m2. So second root is also m1 is m2. So second solution is also m1. See, these two are certainly linearly dependent. They are actually, if you write c1 e to the power m1x and another one is c2 e to the power m2x, they are linearly independent. Sorry, they are linearly dependent. So we cannot consider directly the root solution as c1 e to the power m1x plus c2 e to the power m2x, because this is nothing but c1 plus c2 into e to the power m1x, because m1 is equals to m2. So it makes no sense because it is nothing but a new constant. Okay, so in this case, we have to consider here a multiplier that will be x. If you have two roots are equal, so one one solution will be x e to the power m1x and another solution will be e to the power m1x. Then take the linear combination of that. Likewise, if you have three roots are equal, let's say m1, m2 and m3 are equal. So one will be e to the power m1x, another will be x e to the power m1x, third will be x square e to the power m1x. And then take the combination of all of three. You can further extend this idea. Let's say you have four roots are equal. Then the solution will be one solution will be e to the power m1x, another will be x e to the power m1x, third will be x square e to the power m1x and x cube e to the power m1x. So these are individual solutions. Okay, and take the linear combination to get the contribution from the part where the roots are equal. And rest as it is. Rest as it is means the rest part, that is, if they are distinct, that can be considered as it is, that we have discussed in the last class. So you might have a question now, why these factors are considering here? To make it linearly independent. Idea is to make the solutions as linearly independent. And you can see none of them can be obtained from any of them by a constant multiplier. And certainly, since the order of the differential equation is n, so any factor that you consider for which the power of x is less than n, that is less than, let's say, p, where p is less than n, that will also satisfy the differential equation, because this turn out to be 0 there. So certainly this will not make any change in the differential equation. You can try with we can try with an example. Let's say you have this as the solution. Let's say y is x e to the power x into c1 e to the power m1x plus c2 e to the power m1x. Form the differential equation by eliminating c1 and c2. You can see whatever the differential you can get, solve it again, and then verify whether this is a solution or not. So let me illustrate this one with an example. Then it will be more clear to you. Okay, so then finally I will come to the another possibility, that is case 3. But let us consider first, some of the roots are same. Roots of auxiliary equation. AE means auxiliary equation, okay, that I have mentioned earlier. So let's say you have a third order differential equation. Okay, so here also you start with the consideration that y equals to e to the power mx is a trial solution. Y equals to e to the power mx is a trial solution. If you do so, then you can form the auxiliary equation. So idea is very simple here. If you do the calculation, you can reach to this equation. However, you can remember in this way, just replace d, capital D, the operator d dx by m. So here 3 times derivative is there, so it will be m cube. I mean, for sake of simplicity, just you can remember in this way. Otherwise, you just find the third order derivative, second order derivative, and y, substitute them all to get the auxiliary equation. And I have discussed this one earlier. So if you find the auxiliary equation, you can simply then find the solution. This is nothing but you have to find the solution of an algebraic equation. So I must keep this step. You can verify it. I think all you can verify it. It's very simple how to find the solution of algebraic equation. So if you find the solution, you can look here, the solution of m that you are getting 3 different values of m. Out of that, 2 are equal and 1 is distinct. So distinct is no problem. You can find one solution will be e to the power minus x. Now what about these 2? M is 2. That appears 2 times. So another solution will be e to the power 2x. But what about the third independent solution? That will be e to the power 2x into x. Then consider the combination of all of them to get the general solution. So here you might have a question whether this idea will work here or not. What you do is form the differential equation to verify. Form the differential equation by eliminating these 3 coefficients. Coefficients are C1, C2, or here I have mentioned, I have written them as C1, A and B. Eliminate them to form the differential equation. You will reach to the same equation that I have started with. Okay. So here the idea is we are considering a factor, additional factor, x into the e to the power 2x, that makes sense that because these two solutions in that case will be linearly independent. Okay.
Sir, one doubt, sir.
Yes.
That factor can be of any orders.
No, that if you consider two roots are there, that will be x into e to the power 2x. If three roots are there, one factor will be x, another will be x square. If four roots are there, one factor will be x, another factor will be x square, another factor will be x cube. So it cannot be same as that of the order of the differential equation. It should always be less than the order of the differential equation. So that I have highlighted also in the previous slide, that it will be less than the order of the differential equation. Otherwise, the factor, if you consider any arbitrary factor, it will not satisfy the differential equation. It should always be less than the order of the differential equation, strictly less than.
Sir, I have a doubt how you find the factor.
No, see, you cannot think in that way. You just imagine in this way. See, you have a function e to the power minus x and e to the power 2x. Okay. Is it clear here from these two roots?
Yes, sir.
Now only the only the complexity is e to the power 2x. Right? Because it appears two times. So they are not linearly independent. We are interested to make them independent. So your question may comes in your mind. Let's say you will consider fx into e to the power 2x. That's what you want to ask, right? Why x? Why not any function of x? Right? Now,
yes.
Okay. So when if you substitute that into the differential equation, then you will form a. If you substitute it to the 2x right here, you will have what type of equation you will have? There will be third order derivative here of f, right? Isn't it? Second order derivative will be there.
Yes, sir.
Right? And first order derivative, for some problem, first order derivative will also be there. Yes or no? Yes.
Yes, sir.
So all order derivative will be there. Now, if you consider here, two roots are there, that is x e to the power 2x. Now see, if you substitute that into the equation, whether this will be a solution or not, just substitute that. It satisfies the differential equation or not, just substitute that into the differential equation. Check it, whether it is a solution or not. Do some calculation. See here, third time derivative is there, second time derivative is there. So find all the things and check whether it is a solution or not. And see why it is a solution. Instead considering fx, find, then consider e to the power 2x. I mean some derivation you have to do. And check what is the complexity here to consider fx. Whether for any x it will satisfy the differential equation or not. So I am giving you a homework. It's very good question. Better you know the answer. If you can get the answer if you do the calculation. What you do is check y equals to x e to the power 2x. See whether it is a solution or not. And then check y equals to fx e to the power 2x. It is a solution or not. In order to be this function is a solution, you have to impose some criteria on fx. Whether it will automatically satisfy the differential equation. So if you see the criteria that you have to impose on this f, that if you solve that particular stuff, you will get back this f will always be x. Are you getting my point?
Yes, sir.
Okay. So you have asked me a question. It's very good question. I can give you the answer in a simple way, but better you do the calculation. And then it will be good for you and you will never forget this thing. You choose any function instead of x. Okay. Then proceed, substitute that into the differential equation. Okay. And see for all fx whether it will be a solution or not. Definitely it will not be a solution for all fx. It will be a solution if fx turn out to be a linear polynomial. If you have two equal roots. Similarly, if you have three equal roots, fx maximum can be x square. or x. So that will be less than the number of how many number of roots are equal. Okay, so 3 number of roots are, let's say, equal. Fact f will be second order up to second order polynomial x and x square. So to do that, just listen me. See, I know you have any doubt. Better you listen me first. I am discussing a stuff. You might have a different question. So if you substitute this fx into the differential equation, you can form a relation on fx. From there, you can say, you can conclude fx will be less than second order polynomial for 3 roots. For 4 roots, it will be less than 4 second order, 4 root, third order, and accordingly. Now, Farhan, you ask me the question. Farhan, you were asking a question, so you may ask me now question.
Sir, I think his mic was on by mistake.
Oh, okay.
You said P is less than N, no, sir.
Sir?
So can N be, can P be negative, sir? I mean, -1, -2.
Yeah, that's what I am asking. You know, why positive, negative, different function you are asking. I have considered fx. Fx can be any function. Okay, so it covers your question also. Why not x to the power -1? Why not sin x? Why not cosine x? Why not any other function? Okay, it covers all the answers, right? And another thing is, another point is, don't consider x to the power -1, x to the power -2 always, because see, these are very dangerous function. X to the power -1 is 1 by x. Let's say your domain of interest is includes origin. Okay, then you will have a singularity. At x equals to 0, can you define 1 by x?
No, sir.
No, sir.
So don't consider all those. I mean, not they are not well behaved function. They have many problems with the singularity stuff. They are not differentiable. They can blow up at x equals to 0 if origin includes the domain. Or let's say you are interested to write 1 by x minus 1, and you have the in the domain. See, here we are considering general differential equation, but later on we will consider differential equation with given condition. So domain will be given. So domain is very interesting thing. If domain includes the point where there is a singularity, and 1 by x makes the problem very complicated. So don't consider all those badly behaved functions. Okay. Better we consider always analytic function. Those are differentiable. Okay, like polynomial function, exponential function. Okay, these are well behaved functions. Okay.
Sir, can you please once show the question for e to the power 2x that once?
The slide.
Yes, sir.
Upper slide,
The
sir.
slide is not visible. Okay.
No,
so see
sir.
here. What do you want to see?
No, sir, a little bit up, just the question.
This part.
Yes, sir. Yes.
Okay. I will share you the PPT. Don't worry. Okay.
Sir?
And yes. Any other question?
Sir, if m1 equal to m2 equal to n minus 1, then the general solution will be y equal to